Hello everyone. So in this third video, we're going to compute this very tricky limit. So it's the limit when n goes to infinity of the sum from k equal 1 to n of k over n at the power n. So let's make a few observations. So how to solve this kind of question? Well, the first thing we could try to figure out is how does k over n at the power n grow when n goes to infinity? First easy fact, if you fix n, well, in the case when n is larger than k, k divided by n is strictly less than 1. It's strictly less than a number which is strictly less than 1. And because of that, at the power n, it just goes to 0. Second possibility, what if k grows with n? It means that what if k is never too far from k? For instance, if k is equal to n minus j, for j whatever integer. Well, in that case, k divided by n at the power n is n minus j divided by n at the power n, and we get 1 minus j over n, everything at the power n. And we know that this converges to exponential minus j. Okay, so this gives the following idea. We just separate the sum into two parts. The first one will be the residual terms. For example, we will just take the sum from k equal 1 to n minus 2 minus 1. Okay, we'll just assume that n is even, and if it's odd, we just take n plus 1 minus 2. But it's really irrelevant, actually. It doesn't matter, so we could just, it's not important. So the residual term will give a sum which is small enough so that it will go to 0 when n goes to infinity. And the significant terms, which corresponds to the other k. All right, so let's first deal with the residual terms. So what do we get? If k is between 1 and n over 2, k divided by n is less than 1/2. So at the power n, it's less than 1 over 2 at the power n. And because of that, well, the following sum is less than n over 2 divided by 2 at the power n. N divided by 2 at the power n plus 1 simply goes to 0. So for the residual term, the sum will just vanish at the infinity. Now the complicated part, the significant terms. So what can we see? For the sum from k equal n over 2 to n of k divided by n at the power n, we just change k into n minus j, and we get the sum from j equals 0 to n divided by 2, n minus j divided by n, everything at the power n, which gives the sum from j equals 0 to n divided by 2, 1 minus j over n at the power n. So this term inside of the sum is close to exponential minus j. And in fact, it's always smaller than exponential minus j. Exponential minus j is the general term of a convergent series. And pointwise, when j is fixed, it converges to exponential minus j. So we could use actually the Lebesgue dominated convergence theorem to actually find the limit of this sum. But okay, we can also prove it using elementary means. So let's do that. So the question is, how close is 1 minus j over n at the power n from exponential minus j? Well, this will be a very technical part, so if you want to skip it, you can just go at the end of the video. Okay, let's start. 1 minus j over n at the power n is exponential n log of 1 minus j over n. This suggests to study ln of 1 minus x for x small enough. And in fact, for x between 0 and 1/2, we can check that ln of 1 minus x is minus x squared times a certain function j of x, with j non-negative and less than 1. So when j is between 0 and n over 2, n log of 1 minus j over n is this sum that I wrote here, n times minus j over n minus j squared divided by n squared g of j divided by n, and I just get minus j minus a certain term which I will want to get rid of at some point. So because of that, 1 minus j over n at the power n, I just write the exponential expression, and I get exponential minus j squared over n, g of j squared divided by n squared. And I know that this is supposed to be close to exponential minus j. So I separate exponential minus j, and I get plus exponential minus j times a certain thing, which is supposedly close to 0. So now we try to figure out how close to 0 this can be. In order to do so, I will just take the absolute value of this, and the term between parentheses is negative, actually. So I'll just take the opposite sign, and I get that this is smaller than exponential minus j, 1 minus exponential minus j squared over n, sorry, just because j is between 0 and 1. I can just have this inequality. And we have the well-known inequality, which is 1 minus exponential minus x, just less than x. So this term in blue is less than j squared over n exponential minus j. All right, now I will take at some point the sum from j equals 0 to n over 2. So I can just majorize that by 1 over n times an infinite series of j squared exponential minus j, but this is a finite sum. Okay, this is just a constant number, and I divide it by n. So when n goes to infinity, this just goes to 0. So this is perfect. This is exactly what I wanted. So at the end, what is left in this whole sum? Well, I just separate my sum into 3 terms. I just separate the case when k is between 1 and n over 2. We know that this is close enough to 0. Plus the sum from j equals 0 to n divided by 2 exponential minus j, plus a certain sum which we just computed before. Everything that we've done show that the first and the third term, they go to 0 as n goes to infinity. So when I take the limit when n goes to infinity, I get that the limit of the sum from k equal 1 to n of k over n at the power n is just the infinite series j equals 0 to infinity of exponential minus j. And I can just write it as a geometric series. I write it as 1 over e, everything at the power j. And I know how to compute that. It's 1 over 1 minus 1 over e. So at the end of the day, I get that the limit that I wanted to compute is simply equal to e divided by e minus 1, which is pretty nice and not so easy after all. So a little homework for you. You just change a little bit the limit from the initial limit. You take c, or whatever real number, and the question is, what is the limit when n goes to infinity of the sum from k equal 1 to n of c plus k divided by n, everything at the power n? You can comment the answer if you want. The technique is the same actually that I just did. So the answer is quite close. Thank you very much for watching.